Hello everybody, I welcome you all to my third lecture on time response of control system. My name is Kiran and I am working as an assistant professor in the department of EEE Anits. And my first lecture I discussed what is time response, what is steady state and transient state responses. I also discussed the various standard test inputs, that is step, ramp and parabolic inputs, what is steady state error, and we derived the expression for steady state error, and also discussed the various factors on which the steady state error depends on and their effects. In my second lecture we have done some tutorials based on the various error coefficients, that is Kp, Kv and Ka, and correspondingly we have also found the steady state error for step, ramp and parabolic inputs. In today's lecture we are going to derive the expression for first order control system for unit step, unit parabolic and unit ramp inputs, and later we are also going to derive the expression for second order control system for unit step in various cases. Okay, so now let us consider the first order control system with unity feedback as shown. So applying the elimination feedback rule in block diagram reduction technique, we obtain the transfer function as C of s by R of s is 1 by 1 plus st. So using this expression for unit step, for unit ramp and unit parabolic inputs, we are going to derive the time response expression. First let us consider the unit step time response. Since it is unit step, we know that R of s is equal to 1 by s, and the standard first order system transfer function is C of s by R of s is equal to 1 by 1 plus st. Now if we substitute R of s as 1 by s, which will lead me to C of s is 1 by s into 1 plus st. If I take the t common in the denominator, that will give me the expression of C of s as 1 by t divided by s into s plus 1 by t. So this I will obtain. So upon partial fractions, that will give me a by s plus b by s plus 1 by t. So taking LCM and comparing the coefficients on both sides will give me the value of a as 1 and b as minus 1. Applying inverse Laplace, we all know inverse Laplace of 1 by s is 1 and inverse Laplace of 1 by s plus a is e power minus at. So that will give me the expression as C of t is 1 minus e power minus t by t. The second case, let us consider unit ramp input. Therefore R of s will be 1 by s square. The standard first order control system transfer function is C of s by R of s is equal to 1 by 1 plus st. So if I substitute R of s as 1 by s square, that will give me 1 by s square into 1 plus st. So if I take partial fractions, that will give me a by s plus b by s square plus c by 1 plus st. Here also I can take t as common in the third term, that will give me s plus 1 by t, or else I can keep it as it is your wish. So that will give me the value of a as minus t, value of b is 1 and value of c as t. So now if I take inverse Laplace, so we know that inverse Laplace of 1 by s is 1, inverse Laplace of 1 by s square is t, and inverse Laplace of s 1 by s plus a is e power minus at. So that will give me C of t as minus t plus small t plus capital T into e power minus t by t. And the third case, for unit parabolic time response of first order system, R of s will be 1 by s cube. So we know the standard transfer function of first order system is 1 by 1 plus st. So if I substitute R of s as 1 by s cube, that will give me C of s is equal to 1 by s cube into 1 plus st. Upon applying partial fractions, it is a by s plus b by s square plus c by s cube plus d by s plus 1 by t. Here I have taken t common in the denominator. Okay, now I am taking LCM, and if I compare all the coefficients on both sides, that will give me a value as t square, b value as minus t, c value 1, and d value minus t square. Okay, so upon inverse Laplace, we know that inverse Laplace of 1 by s is 1, inverse Laplace of 1 by s square is t, inverse Laplace of 1 by s cube is t square by 2, and inverse Laplace of 1 by s plus a is e power minus at. So that will give me C of t as t square, here inverse Laplace is 1, minus capital T into small t, since inverse Laplace of 1 by s square is t, plus t square by 2, since inverse Laplace of 1 by s cube is t square by 2, and minus t square into e power minus t by t, because here inverse Laplace of 1 by s plus a is e power minus at. Now coming to second order control system. So this is the standard form of second order closed loop transfer function, which is C of s by R of s omega n square by s square plus 2 zeta omega n into s plus omega n square, where omega n is natural frequency of oscillation and zeta is damping ratio. So according to the range of zeta, we classify various second order control systems. So if my zeta is 0, my closed loop poles are purely imaginary, and the nature of response will be with oscillations with constant frequency and amplitude, and we can classify that as undamped second order control system. If zeta lies in between 0 and 1, the closed loop poles are complex conjugate with negative real part. We'll have damped oscillations, and that I can classify as underdamped second order control system. If zeta is equal to 1, the closed loop poles are real, equal, and negative. The nature of response is purely exponential, and that I can classify as critically damped second order control system. And the fourth case, if zeta is greater than 1, the closed loop poles are real, unequal, and negative. The nature of response is exponentially sluggish, and that I can classify as overdamped second order control system. So now we are to derive the response of second order control system in all these four cases. Okay. So first let us derive the expression for time response of undamped second order system for unit step input. So since it is undamped, we all know that zeta value is 0. So this is the standard form of second order closed loop transfer function. Since zeta is equal to 0 and it is unit step, R of s is equal to 1 by s. So that will give me C of s as omega n square by s into s square plus omega n square. So upon partial fractions, that will give me a by s plus b by s square plus omega n square. So the value of a and b are 1 and minus s respectively. Okay, so applying inverse Laplace, that will give me 1 minus cos omega n into t, because the inverse Laplace of 1 by s is 1, the inverse Laplace of s by s square plus omega n square is cos omega t. So that is the reason I have obtained the expression for C of t as 1 minus cos omega n into t, where omega n is the natural frequency of oscillation. The second case is the underdamped second order control system for unit step input. Since it is underdamped, zeta lies in between 0 and 1, and the standard equation we know that it is omega n square by s square plus 2 zeta omega n into s plus omega n square, isn't it? So the denominator polynomial roots, if I find, it is minus zeta omega n plus j into omega n into root over 1 minus zeta square. So here I'll assume zeta omega n as alpha and omega n into root over 1 minus zeta square as omega d. Since it is unit step input, R of s is equal to 1 by s. So we know the standard form of the second order system, isn't it? So it is omega n square by s square plus 2 zeta omega n into s plus omega n square. So if I substitute R of s is 1 by s, that will give me C of s as omega n square by s into s square plus 2 zeta omega n s plus omega n square. So upon partial fractions, that will give me a by s plus bs plus c by s square plus 2 zeta omega n into s plus omega n square. Since it is a quadratic equation, I am getting as bs plus c. So if I take LCM and compare the coefficients on both sides, I get a value as 1, b value as minus 1, c value as minus 2 zeta omega n. So since zeta omega n is alpha, that will give me the expression for C of s as 1 by s minus s plus 2 alpha divided by s square plus 2 alpha s plus omega n square, because this zeta omega n is alpha, here zeta omega n is alpha. The denominator polynomial, that is s square plus 2 alpha square plus omega n square, this I can rewrite as s square plus 2 alpha s plus alpha square plus omega n square minus alpha square. Simply I have added and subtracted alpha square. The first term, the first part, that is s square plus 2 alpha s plus alpha square, this I can write as s plus alpha whole square, isn't it? So the denominator polynomial becomes s plus alpha whole square plus omega n square plus alpha minus alpha square. But again, alpha is nothing but zeta omega n, isn't it? So that will give me s plus alpha whole square plus omega n square minus zeta square omega n square. If I take omega n common from second and third terms, that will give me s plus alpha whole square plus omega n square into 1 minus zeta square. Okay, but omega n square into 1 minus zeta square is nothing but omega d square, which we had seen earlier. So that will give me the expression of C of s as 1 by s minus s plus 2 alpha divided by s plus alpha square plus omega d square. So now we have to in order to apply inverse Laplace, everything should be in the standard form. We know the equation, the formula, that is inverse Laplace of s plus a by s plus a whole square plus omega square is equal to e power minus alpha at into cos omega t, and also inverse Laplace of omega by s plus a whole square plus omega square is e power minus at into sin omega t. So this second term, I need to bring this second term in these two standard forms, isn't it? So in order to bring those in those two standard forms, the numerator s plus 2 alpha I will rewrite as s plus alpha plus alpha. That is the reason here I have obtained 3 terms, isn't it? this is actually in the standard form 1 by s. The second term is also in the standard form. It is s plus a divided by s plus a whole square plus omega square. But the third term is not in the standard form. So it is in the numerator of the third term, I need an omega d in place of alpha. So I'll just multiply and divide the third term by omega d, which will give me the third term in the standard form, that is omega d divided by s plus alpha whole square plus omega d square. So this I have taken as common, alpha divided by omega d. Now if I apply inverse Laplace, that will give me the expression for c of t as 1 minus e power minus alpha t into cos omega d into t minus alpha by omega d into e power minus alpha t into sine omega d. So we can still reduce the obtained expression. Here in place of alpha, I will substitute zeta omega n, and here also in place of omega d I will substitute as omega n into root over 1 minus zeta square. So if I take, so as you can see clearly that e power minus zeta omega n is common in the second and third terms, isn't it? So if I take e power minus zeta omega n into t divided by 1 root over 1 minus zeta square, common from both second term and third term. Since this term is not present in the second term, I'll get that when I take as common in the second term. The only term that is left here is cos omega t. Okay, in the third term, since here omega n will get cancelled, since I have e power minus zeta omega n divided by 1 minus root over 1 minus zeta square, so I'll get the value as zeta into sine omega d. This I will compare with this expression, that is sine omega dt plus theta is equal to sine omega dt plus cos theta plus cos omega dt into sine theta. If I compare these two expressions, I can conclude that zeta is nothing but cos theta and sine theta is nothing but root over 1 minus zeta square, isn't it? Because since I have this term, let me clear this in order to make you this clear. Since because here I have cos omega dt, here also I have cos omega dt. Therefore, sine theta is nothing but equal to 1 root over 1 minus zeta square. Here I have sine omega dt term. Here also I have sine omega dt. So obviously cos theta will be nothing but zeta. Okay. So this I can rewrite my expression as c of t is equal to 1 minus e power minus zeta omega n into t by root over 1 minus zeta square, which I have taken as common, into sine of omega dt plus theta, where this zeta is nothing but, as we know, damping ratio, omega n is nothing but natural frequency of oscillation, and omega d is called damped frequency, which we know is represented as omega n into root over 1 minus zeta square, and theta is tan inverse of root over 1 minus zeta square by zeta. So the third derivation is overdamped second order control system. Since it is overdamped, zeta value is greater than 1. We know the standard form of second order closed loop transfer function, that is C of s by R of s is omega n square by s square plus 2 zeta omega n into s plus omega n square. So if I assume the roots of the denominator polynomial as sa and sb, it is nothing but minus zeta omega n plus or minus omega n into root over zeta square minus 1. So here I will assume s1 as minus sa and s2 as minus sb. So that will give me S1 as zeta omega n minus omega n into root over zeta square minus 1, and S2 as zeta omega n plus omega n into root of zeta square minus 1. So now the given expression C of S by R of S can be rewritten in terms of S1 and S2, isn't it? Since the roots are S1 and S2, we can write them as omega n square by S plus S1 into S plus S2. Since our input is unit step, R of S is equal to 1 by S. That will give me the expression of C of S as omega n square divided by S into S plus S1 into S plus S2. Upon partial fraction, that will give me A by S plus B by S plus S1 plus C by S plus S2. So upon taking partial LCM and comparing the coefficients on both sides, A value is omega n square by S1 S2, B value is omega n square by minus S1 into S2 minus S1, and C value is omega n square by minus S2 into S1 minus S2. Okay, so here we know the values of S1 S2, isn't it? So I'll substitute the values of S1 S2 in all the A, B, C values that we have obtained. So this is S1 and this is S2, isn't it? So A plus B into A minus B is, we know, A square minus B square, isn't it? So that will cancel these two terms, and I'll be left with omega n square by omega n square. That will bring my value of A to 1. Now coming to the value of B, S2 minus S1, if I do here, that will again make my expression of B as minus omega n divided by S1 into 2 into root over zeta square minus 1. And similarly in the value of C, if I substitute the values of S1 and S2, that will ultimately bring my value to omega n divided by S2 into 2 into root over zeta square minus 1. So now here these are the values of A, B, C, the modified values of A, B, C that I have obtained, and now if I apply inverse Laplace, isn't it? So the first term is anyhow 1 by S, isn't it? So inverse Laplace I can easily identify. Okay, so this entire thing is a constant. Okay, so the second term is in the form of 1 by S plus A, isn't it? In the third term also this is constant, and this is also in the form of 1 by S plus A. So upon inverse Laplace, that will give me the first term becomes 1. This entire thing is a constant, so as it is I'll get that expression. So inverse Laplace of 1 by S plus S1 is e power minus S1 into t. This term is brought as it is, and inverse Laplace of 1 by S plus S2 is e power minus S2 into t. So if I simplify further, in both the terms omega n divided by 2 into root over zeta square minus 1 is common, so I'll bring that out, and that will give me 1 minus omega n by 2 into root over zeta square minus 1 into e power minus S1 into t by S1 minus e power minus S2t divided by S2. So this is the expression for the overdamped second order system for unit step input. And the last case is critically damped. Last case is critically damped second order system for unit step. That is zeta value is 1, isn't it? We know the standard form of second order closed loop system. And if I substitute zeta as 1 and R of S if I substitute as 1 by S, that will bring me to the expression of C of S as omega n square by S into S plus omega n whole square. upon partial fractions, that will give me a by s plus b by s plus omega n plus c by s plus omega n whole square. That will give me the values of a as 1, b as minus 1, c as minus omega n. So this I can apply inverse Laplace, isn't it? So this because everything is in standard form. The first term becomes 1. The second term will become e power minus omega n into t. The third term will become omega n into t into e power minus omega n into t. So further, if I take common e power minus omega n into t common from the second and third term, that will give me the expression as 1 minus e power minus omega n into t into 1 plus omega n into t. So this is the time response of all the 4 cases. That is, the first case we have seen undamped, the second case we have seen underdamped, the third case we have seen overdamped, and the fourth case we have now seen critically damped. So this concludes my today's lecture on time response of control system. We have derived actually the expression for time response of first order system for unit step, unit ramp and unit parabolic inputs. Also we have derived the second order response, time response of 4 cases, that is undamped, underdamped, overdamped and critically damped control systems. Thank you.